Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a very nice equation with complex numbers. If you like algebra number theory and trigonometry problems, you can also go ahead and check out my other channel, which is Cyber Math, that is Cyber with an S. I also have a shorts channel which I publish once a week. Anyway, so here's the problem. We have A plus BI, which is a complex number, by the way. It's also the name of this channel, to the second power equals b plus ai. So what kind of number can be reversed, if that's the right term, when we square it, right? Maybe some of you already recognize this, but I'm going to show you 3 different methods to approach it. All right, great. Let's start with the first method. For my first method, I'm going to start by setting this equal to z. So suppose z is equal to a plus bi. So here's my goal. My goal is to find b plus ai in terms of z. In other words, I kind of start with this a plus bi is equal to z, then b plus ai looks like what, right? In terms of z, of course. How can I do that, right? First of all, I didn't know how to do this, so I tried the following. First, I look at the complex conjugate, which is by negating the imaginary part. So a minus bi is called the complex conjugate of a plus bi, because when you multiply them, you get a real number. When you add them, you also get a real number. And that number is unique. Okay? But this doesn't give us b plus ai. Here's what we can do. Maybe take this number and multiply by something. So here's the second thing that I tried. If I multiply z by I, that's going to give me I times a plus bi. By the way, something that I forgot to say all the time. I squared is -1 because I is considered the square root of -1. Okay? It's the principal square root because there are 2 square roots. So when you multiply a plus bi by I, you get ai plus bi squared. But because I squared is equal to -1, this gives you ai minus b, or negative b plus ai. So iz is equal to negative b plus ai, and I do need b plus ai. So what can I do? Well, first of all, I can go ahead and negate this. So if this is iz, negative iz would be b minus ai. So we multiply both sides by -1. We're so close, aren't we? We do need b plus ai, so I do need to take the complex conjugate. So the complex conjugate of negative iz is going to give me b plus ai. So to answer that question, if a plus bi is equal to z, then b plus ai is the complex conjugate of negative iz. So we had to do so many things to reverse a and b. And if you think about it geometrically, we have the z here like a plus bi, and you kind of give it a little rotation so that you can switch to a and b values. But in fact, you're actually doing the following. If this is theta, this is also theta. So the argument after the rotation is actually pi over 2 minus theta. So you have to turn it how many radians? Pi over 2 minus 2 theta radians in that direction. You can also look at it geometrically that way. Okay? Great. Now, since we got this type of equation, we have the following from here. Oh, by the way, how do you simplify the complex conjugate of negative iz? Let's go ahead and simplify that. Well, conjugacy is interesting because it has some identities. For example, if you try to conjugate a product, you can actually do the terms separately or the factors separately like this. What is the complex conjugate of negative I? It's 0 minus I, so it's going to be 0 plus I, which is I, and this is just going to be I times z bar. So, in other words, we have the following. If a plus bi is z, then b plus ai is I times z bar. And you can always test it out. Now, let's go ahead and put it into our equation. We had a plus bi to the second power equals b plus ai. So I'm going to go ahead and replace a plus bi with z, so it's going to be z squared. And the b plus ai is just going to be I times z bar. How nice, right? We got a nicer equation because there's no a and b. We only have z and z bar. Now, how do you solve an equation like this? That's a good question, right? And the best way to approach it, in my opinion, is to replace z with its polar form. Thanks to Euler, we have r e to the I theta for a complex number, which is, by the way, equivalent to r times cosine theta plus I sine theta, because thanks to Euler, we have the most beautiful equation, which gives us e to the I theta equals cosine theta plus I sine theta. Of course, r stays, right? So this means that if you have a complex number that makes an angle of theta with the positive real axis, which is the x-axis in this case, let's call that theta. That's the argument. And r is the absolute value of our number. And our number is represented by a dot, a point, or a vector. Okay? Makes sense? Geometrically, that's what it is. But we're going to use the more compact form, which is r times e to the I theta, because it's a lot easier to exponentiate. Imagine you try to raise this to the 10th power. Raising this to the 10th power would be a lot easier, don't you think? If not, then go ahead and test it out. Now, we have z squared. How do you find z squared from here? If z is equal to that, z squared would be r squared e to the power I theta multiplied by 2. That's going to be 2I theta. And on the right-hand side, we have I times z bar. If z is this, z bar is just going to be obtained by negating the angle. Because if you think about it, if this is my complex number, again, a little bit of geometry. If this is my z, then z bar is just obtained by negating the imaginary part. Therefore, it's just going to be the negative theta. Okay? So that's all you have to do. Now we got a super duper interesting equation. This is what we have now. Okay? That's the equation we need to solve. And how do we solve it? Let's go ahead and talk about this equation. All right? So I'm going to do a little bit of something here. For example, first, I want to replace I with e to the power I times pi over 2. Again, Euler coming to the rescue. Multiply by r, multiply by e to the power negative I theta. I'm going to go ahead and put these two together because they're both exponentials, and write the r first and r squared here. R squared e to the 2I theta equals r times e to the power I times pi over 2 minus theta, which is kind of like changing the sine and cosine, if you ask me what it does. And that's the equation we are getting. Alrighty? Now, from here we get two things. Either r is 0 or r is not 0. Why? Because if you compare the moduli, or the absolute values, you get r squared equals r, which implies r times r minus 1 equals 0, which means r is 0 or r is 1. If r is 0, z is 0, that's the only number, and obviously z equals 0 is a solution because 0 squared equals 0. Right? That works. But we're not looking for trivial solutions. We're looking for non-trivial solutions. Let's go with r equals 1. If r is equal to 1, from here, we get e to the 2I theta equals e to the I times pi over 2 minus theta. And of course, you can kind of drop the i's here and kind of write this as 2 theta equals pi over 2 minus theta. But here's the catch. You have to make sure that you include all multiples of 2 pi, because two angles can have the same value, same exponential, same sine, cosine, when they differ by a multiple of 2 pi, right? Because 2 pi just gives it a rotation and brings you basically to the same point on the unit circle. Great. Now let's go ahead and put the thetas on the same side. This will give you all the solutions. And then from here, of course, n is an integer, I guess needless to say, right? But I still said it. Theta equals pi over 6 plus 2 pi n over 3 from here. Now, what am I going to do with this, right? We're going to go ahead and replace n with 0, 1, 2, and 3. If you replace n with 3, that's just going to give you an additional 2 pi, so you don't really need that. But you can go ahead and use n equals 0, 1, and 2 here. Let's go ahead and take a look at each one. If n is equal to 0, theta is going to be pi over 6. If n is equal to 1, you're going to get pi over 6 plus 4 pi over 6, which is 5 pi over 6. And then you're going to get 9 pi over 6, which is 3 pi over 2. So we got three angles, right, for our argument. And if you look at each one of these, and remember that r is equal to 1, so z is going to be e to the power I pi over 6. By the way, this can be written as cosine pi over 6 plus I times sine pi over 6. And if you look at the values, this is going to be cosine of 30 degrees, which is root 3 over 2, plus 1/2 times I. For the second theta value, for 5 pi over 6, you're going to get, if you think about it, they actually differ by pi. So it's going to be in the second quadrant. You're going to get a negative cosine, but the same sign. So it's going to look like this. And then finally, for pi over 2, it's just going to be negative I. And if you go ahead and actually plug it in, you're going to realize for a equals 0, b equals negative 1, this is actually going to work. Okay? So that's basically the first method. I know it took a while to solve this problem, but let's go ahead and take a look at the second solution and then the third one real quick, hopefully if you have the patience, right? Okay, great. So we're going to start with this something we already know. Z squared is equal to I times Z bar, okay? How am I going to proceed with that? First of all, by the way, if you go ahead and put these into a cubic equation, along with Z equals 0, of course, Z equals 0 is another solution, so there are 4 solutions. You're going to get Z times Z cubed minus I equals 0. I want you to pay attention to that quartic equation because we're about to get that, okay? So I'm going to go ahead and multiply both sides by Z squared, and that's going to give me this. And left-hand side is going to be Z to the 4th power. Now I'm going to go ahead and separate one of these Z values here. Now Z times Z bar is just going to give us the absolute value of Z squared. Let's go ahead and write it that way. It's going to be I times absolute value of Z squared times Z. So this is the type of equation we're getting. Now, how do you simplify something like this? I do need to know the absolute value, but from earlier, we do know it's equal to 1. But let's go ahead and prove that one more time because it's fun. So we know that Z squared is equal to IZ bar. Let's go ahead and take the absolute value on both sides. By using the properties of absolute value, this can be written as follows. You can go ahead and separate these. And as you know, the absolute value of Z bar is the same as absolute value of Z. Absolute value of I is 1. So now we get the following. And from here, we get 2 solutions again. Absolute value is 0 or 1, but absolute value of 0 equals, gives us Z equals 0, which is not that interesting. And this one gives us what we're looking for. If you go ahead and replace absolute value of Z with 1, you get IZ from here. And guess what that gives you? Z to the 4th equals IZ, which is the same as this one, which is kind of interesting, don't you think? Great. Now, let's continue with the third method. The third method is actually something that people commonly use for these kinds of equations. Of course, if you had the 3rd power, 4th power, even 10th power, you probably wouldn't want to use this, right? Because that would take forever. But with the 2nd power, this is pretty doable. So I'm going to go ahead and expand left-hand side. It's going to give me a squared. Remember, this is minus b squared plus 2abi equals b plus a. Of course, if 2 complex numbers are equal, their real parts are equal and their imaginary parts are equal. Let's start with this one because this is easier to solve. 2ab equals a. I'm going to go ahead and factor it, put everything on the same side. Factor out a. You get 2b or not 2b. Yay. I like that. 2b minus 1 equals 0. And then from here, you get 2 things. A is equal to 0. But if a is 0, then b is 0, I think. Or I could check. Or b is 1/2. Now, let's go ahead and look at the second equation, which is a squared minus b squared is equal to b. If a is 0, we're going to get b equals 0 or b equals negative 1. So from here, b is 0 or b is negative 1. If a and b are both 0, that gives us z equals 0. If a is 0, b is negative 1, that gives us negative I. And remember, that was one of the solutions that we found from 3 pi over 2 as our radian. Remember, as our argument. So both of these solutions are good. What about b equals 1/2? Let's go ahead and plug it in because this is going to be more interesting. If b is 1/2, this is going to be 1/4. This is going to be 1/2. From here, a squared is going to be 3/4. If you square root it, you're going to get 2 values, root 3 over 2 and negative root 3 over 2, along with b equals 1/2. This is going to give you the 2 solutions we already talked about. Z is equal to 1/2 plus root 3 over 2i. And z is equal to negative 1/2. Oops, I meant 1/2 minus, wait a minute. Did I mess up? Okay, sorry, I switched these around. It's supposed to go root 3 over 2 first, plus 1/2 of I, and then negative root 3 over 2, plus 1/2 of I as the solutions. So those are going to be all the solutions. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out Cybermath, the Shorts channel, and A+BI, and bye-bye.